with just x squared minus 4, right? Since we might say x squared is bigger than 4 for this range. And then this becomes the limit as x approaches 2 from above, of just 1 over x plus 2, because now the x minus 2 factors cancel. And as x approaches 2, we get 1/4. So that's the first limit. And then the next limit is much the same, but now we're approaching x equals 2 from the left. So now we're moving in this direction, 2 to the left. So we write just, where's our, so just plug it in right directly. So x minus 2 over x squared minus 4 absolute value. Okay, so we want to replace the absolute value, and now we're going to use the fact that x is less than 2. So the x squared minus 4 in the range that we're considering is going to be negative. So we're going to replace the absolute value with negative x squared minus 4. All right? So that's since x squared is less than 4, and we might also say since x is bigger than 0. We don't need to concern ourselves with values of x which are far negative, because we're only interested in x approaching 2. Okay, so the x squared minus 4, we know that factors as x minus 2, x plus 2. So this thing is going to, right, equals, replace it with something that it's equal to. The x minus 2, well, maybe we'll even write down those factorizations. Why not make it very clear what we're doing? All right, there's the factorization, and now we'll write it simplified with the cancellation. So we get 1 over minus x plus 2, and that's minus 1/4. So we have minus 1/4 there, we have plus 1/4 there. These two things are equal, so since the limit as x approaches 2 from the right of f of x does not equal the limit as x approaches 2 from the left of f of x, the left and the right hand limits are not equal, we conclude that the limit as x approaches 2 of f of x does not exist.
How many marks was your question worth?
That was worth, yes, we didn't say, that was worth 2 marks. Okay, we've laid it out in quite a lot of detail here, but the essence is that we have to consider these 2 separate cases coming from the 2 possible things that can happen to this absolute value, and noting that the 2 limits are different. This is plus 1/4, that's minus 1/4, so the function is not approaching the same values on either side. Here it would be approaching 1/4, and on this side it will be approaching minus 1/4, something like that. And, those values are not the same, so the limit doesn't exist.
Good. And what's f of 2?
What's f of 2? Well, that's a good question. If we plug x equals 2 in, we get 0 over 0. That doesn't make much sense. So in fact, this function is not really defined at x equals 2. If there's a denominator that gets to be 0, then the function's not defined at that particular value. And in this case, there's nothing we could define it to be to make it continuous. If we wanted to try to make it continuous by defining f of 2 in some special way, it wouldn't work, because no matter what we do, these 2 limits aren't going to be equal.
Yeah, so if we did have these 2 limits equal, and yet the function was undefined, we could just define the function, and that's kind of what we did with sine of, what is it, sine of 1 on x? Sine of x over x, was that the one? Yeah, sine of x over x. We kind of, on the face of it, it's not really defined, but as x gets to 0, then we just define it to be 0 around it. It's this nicely defined function. So even though and it's this limit being equal from both sides, which allows us to do that. But in this case, the limit's just not, there's no way this function can be continuous. Good, but then look, that's what you would write in your exam, and we're just talking about continuous functions at this point because we like continuous functions. Good. My turn. This is a 2-mark question. Determine the limiting behavior of some set group of functions over here over some other functions, all da da da. And the method as x goes to infinity. X to infinity. So that's the limit we're talking about. The way you do all these questions where you've got a kind of ratio of functions is you divide by the highest power in the denominator. That's so important, I'm just going to write it down. So our limit is, well, that's the limit as x approaches infinity of, now I want to divide through by the highest power of the denominator. I do that to the top and the bottom, so this is e to the negative x on x squared plus 3 minus 2 on x squared over 4 plus 3 on x plus sine x over x squared. Like that. Good. Now I've got a nice 3 and a 4 here. Something has to happen with these other things. Fortunately, as x gets very large, these things all go away. So I might just write down that because lim goes to infinity of e to the negative x over x squared is 0, as is this one, of negative 2 on x squared, and this one as well. So that's 3 on x is equal to 0. They're all equal to 0. So I can just say that this limit, and this limit are equal to 0. That's appropriate. This one I have to work a little bit harder for to get the limit of sine x on x squared equal to 0. For that I'll need to break out a theorem. So and since let's do this as negative 1 on x squared is less than or equal to sine of x over x squared is less than or equal to 1 on x squared for all x. Since this is true for all x, I've got this function here. This function sine x on x squared is bound below by something, bound above by something, and the limit as x approaches infinity of negative is equal to the limit as x goes to infinity of this thing is equal to the limit as x goes to infinity of this thing, 0, then the limit of this function as x goes to infinity gets pinched and it goes to 0 by the pinching theorem. Good, so I had to work a little hard to get this bit divided by x squared to be equal to 0, but now I can just say that the limit as x goes to infinity of f of x is equal to the limit as x goes to infinity of these things, e to the negative x on x squared plus 3 minus 2 on x squared 4 . And now I just apply the limit to each of the things inside. So that goes to 0, so I can put a cross through that. That goes to 0, that goes to 0, that goes to 0, that goes to 0. I just get left with 3 over 4.
Yep. So a little bit subtle here to deal with this particular thing because of the oscillation of the sine x, but the pinching theorem deals with that.
It's a bit sneaky the way that the pinching theorem kind of appears in this question.
Mm.
Normally this would be a 1 mark question, where if it didn't have the sign in it, this would be a 1 mark question, but the presence of the sign makes the question a little bit harder.
Yeah. He says it's not entirely obvious kind of limit because it bounces around from being positive or negative, but the point is that it's still constrained by these bounds of 1 on x squared and it's negative.
Thank you very much, pinching theorem.
Yes. All right, so this question here, this next one is one where we have two functions. F of x is x squared plus 4, and g of x we're told is 1 over square root x plus 1. And we're asked to give the explicit forms of f circle g of x and g circle f of x. So we have to recall the meaning and definition of these composite functions. So let's just write down what we need. So the first one, f circle g of x. Clearly the first thing we need to do is to express our understanding of what this actually means. What is the composite f circle g? Well, it means f of g of x. Okay, we're taking f of g of x. So given the input x, what we're doing is we're applying g first, and then after we've done that, we're applying f to the result of getting g of x. Okay, so let's do this in 2 steps. So the first thing I'm going to do is going to replace the g of x with what it's equal to. So this is f of, we're told that g of x is 1 over square root x plus 1. And now I only have f to worry about. So this is f of x is x squared plus 4. So if we're inputting this, we have to take 1 over square root x plus 1. We have to square that and add 4. Well, that's not too hard. That's going to be 1 over x plus 1. We square the square root plus 4. And we could leave it like that, or maybe we could clean it up and put things over a common denominator. There'd be a 4x plus 4 and plus 4x plus 5 altogether over x plus 1. So that's the composite in that direction. And in the other direction, it's the same kind of story. We're just doing it in the other way. So g circle f of x is g of f of x. We'll write down the definition first, making clear that we know what we're talking about. And now the f of x is going to be substituted first. So this is g of x squared plus 4. So I'm doing it in 2 steps so that I'm doing this systematically and I'm not going to get confused. And now the g of something is 1 over the square root of that something plus 1. So it's 1 over the square root of, and I have to replace the x up there with x squared plus 4 plus 1. So in the formula for g, I'm just replacing the x with x squared plus 4, and I get 1 over square root x squared plus 5. In particular, we see that the composite in this direction is different from the composite in this direction.
Excellent. It's a bit like brushing your teeth and eating breakfast, this function of g of f and f of g. It's, you get different things when you do these operations in different orders. So I always have to eat breakfast first. That's the first thing I do in the morning. Breakfast first, then teeth brushing.
Well, health experts sometimes think that it's better to brush your teeth first and then have breakfast. So maybe while Daniel's doing that, maybe I can see here that we're not writing down a lot of things, right? We're writing down the minimal amount that's required so somebody can follow the argument. That's really what you're aiming to do when you're writing a test. You want to express yourself in as efficient and concise a way, but so that still that somebody can follow the argument and can see clearly what it is that you're doing.
Yeah. There was a question in the comments about the previous limiting question and whether it was how do you know to use the pinching theorem to show sine of x on x squared is equal to 0, and do you need to do that every time? My feeling is it's partially based on how many marks the question is worth. So if this was a 10-mark question and the only question you got on your exam was that question and you had 20 minutes to do it, I'd prove all of those limits by the pinching theorem. I'd prove 2 on x squared was equal to 0 by the pinching theorem. I'd do the whole thing. Because I've got 4 minutes, I'd prove, I guess, the most complicated of those things using the pinching theorem, and that's just the sine of x on x squared. It's really how much math can I get down in 4 minutes, rather than, I mean, you could debate that it's required to prove all of those limits using the pinching theorem. We just said in my 4-minute version of it, 3 of them were 0 and 1 of them was kind of a bit tricky, so I used a theorem to prove it. Norman, do you have thoughts on this?
Yeah, I mean, another alternative might be to say, that, well, we've learned that the limit of sine x on x squared is equal to 0, maybe from the online tutorials where we did some kinds of questions like this. So, if you draw upon some prior information or knowledge, I think that could also get you by. So it is a bit subjective. I think, as Daniel says, you have to tailor the amount of work that you're doing to how much the question's worth. It's sort of sensible. Yeah, you want to do a reasonable amount of work, but not much more.
Good. So I have a question about the intermediate value theorem. So we're given some polynomial, and we're told straight up to use the intermediate value theorem to show that this polynomial has a root somewhere between -2 and 0. The first thing I'm going to do is find out what p of -2 is and p of 0. P of -2, well, that's just -8 minus 3 times 4, which is 12, plus 8 plus 2 is -10. Good. And p of 0, well, that one's easy, that's just 2. Good. So I've got my function being -10 when x is -2 and being 0 when x is equal to 2. Intuitively, the intermediate value theorem tells you that you've got a continuous function. It's negative on one side, it's positive on the other side. It must have crossed the x-axis somewhere, but that's not what we'd write. We'd write it a bit more formally than that. So, since p is continuous on the interval, closed interval -2 to 0, right? This is what the intermediate value theorem requires in order for you to conclude something. You have to have a continuous function on some interval. This is the input to the intermediate value theorem. That tells you that for every, say, z in the range -10 to 2, there is some c in the range -2 to 0 p of c is equal to z. This is pretty much what the intermediate value theorem tells you. So we've got a continuous function, we've got this interval. For every z in the range of the function restricted to this interval, so the z values can be between -10 and 2, there is some value in the domain such that p of that value, p of c, is equal to that z. So I can pick z to be equal to -9, 8, or -8, 2, or in our particular case, I pick z to be 0. Since 0 is in this range, or is in the interval negative 10 to 2 is some c in the range negative 2 to 0 p of c is equal to 0, which is exactly what the question asked us to prove. I might say, since there is some c, there is, by the intermediate value theorem, since they told me to use the theorem, I better be very clear that I'm using it down here. I mean, technically, this is the intermediate value theorem, so even though if I forgot to call it that name, I've clearly used the intermediate value theorem, so I'm not too fussed about whether or not that was explicitly stated, but it's a good idea to just let them know that, hey, I use the intermediate value theorem to do this.
Yeah, I think, again, there's a picture that one could draw here, but one doesn't really want to spend a lot of time drawing this picture. But the basic idea is that you have some cubic curve, typically cubics go like this, and it's taking on value minus 10 at one point, and it's taking on the value 2 at some other point. So somewhere in between there, it's going to cross, well, any intermediate line, but in particular, it's going to cross a 0. So there's an easy sort of geometrical meaning for it. This intermediate value theorem is really kind of intuitively clear
for continuous functions.
For continuous functions.
Which is, I'm just going to put my marker's hat on for a moment and get my red pen. If I was coming across this and I was going to mark it, the things I'd be looking for are this. I want to know, does the student know the intermediate value theorem? And that the student needs to know that p is a continuous function on some closed interval. I'd be looking for that. I'd also be looking for this value and this value here. So a student who writes this, this, and this is going to be pretty much on the right track. I want to know, do they know what the intermediate value theorem is, and are they applying it correctly? Those are the two things I'd really be looking for as a marker coming onto this question.
Yeah. If the question was on a final exam, maybe worth a little bit more. I mean, the fact that Daniel's solution here is well laid out sort of as an English paragraph, you can sort of see there's some logic to it. It's not just disjointed formulas. There's some sense, it's sort of an argument, since p is continuous, this is that, there's a logic. And so I think that's also an important something to strive towards, to try to write, not in really flowing prose or anything, but write a story, write an explanation with more or less continuous sentences, especially with a question like this where you're asked to show something, or there's some kind of proof or argument that's being asked for.
People like Norman and I like that, because we read a lot of exams, and it's nice when we read something which reads well.
Yeah. Okay, so for this question, it's also about continuous functions, although it maybe doesn't say so. It says, consider the function f of x equals minus cos x on the interval minus pi over 2 to pi over 2. And it's important to note that this is an open interval. Determine whether f attains a maximum value on the interval. Give reasons for your answer. Okay, so first thing I'm going to do over here is just to draw a little picture. Okay, cosine x, well, let's draw cosine x first just to orient ourselves. So we know that cosine x does something like this. It goes from 1 to minus 1, and here it's pi, and here it's minus pi. There's a complete cycle of 2 pi. And here it's 0 at pi over 2 and at minus pi over 2. Okay, so if we were then interested in, so that's y equals cosine x, and if we wanted to graph y equals minus cosine x just on the interval that we're interested in, from minus pi over 2 to pi over 2, then, and the open interval is what we're considering, then we just have to negate this thing, sort of reflect it in the x-axis here. And we would get something like this, okay, down to minus 1. So this would be the graph of y equals f of x. Okay, so now intuitively we can see what's happening. What we're asked for is whether or not this function on this particular open interval actually attains a maximum value. So we have to, first of all, know what that means. And it means that, well, let's actually write it out what it means. So let's recall that f of x attains maximum value on an interval, say I, if there is a c in that interval I such that f of c is bigger than or equal to f of x for any other x, or for all x in the interval I. Alright, so that's what it means to attain a maximum value. It means that can you find some value c somewhere in the interval in question so that the function's values at that c are bigger than or equal to the function's values at all other points in that interval.
So can I mention here that this is different to finding an upper bound on the function. So I could have chosen f of 1, or just y equals 1 as an upper bound on this function. But that's not a maximum because the function never reaches 1. To have a maximum, the function has to be bound by it, but also reach it.
Yes, so we're looking actually for a point in the interval in question for which the function has a maximum at that point. And I think we can see here that that's not going to happen because geometrically the function's values are going to be getting closer and closer to 0 as we move towards pi over 2 or to minus pi over 2. But we don't actually ever get to 0 because, well, the points pi over 2 and minus pi over 2 are excluded from the interval in question. Okay, so so our function, f of x, does not attain maximum value since f of x is always less than 0 on this interval. So we can see that it's always less than 0. And the limit as, say, x approaches pi on 2 from the left of f of x equals 0. In other words, f approaches the value 0, but does not attain it. Oh, so we can just stop there. F approaches the value 0, but it does not attain it. So in this question, we've drawn a picture. I think the picture helps the argument in this case. Sometimes it is useful to draw a picture. And we've also demonstrated that we know what the question's about. We've written out a definition, and then we've sketched the argument for why it actually works in this case.
Cool. All right. So I might just mention that this bit here where you show the limit approaches 0, that's important because it's establishing that you can't choose an upper bound for this anything lower than 0. So we could dismiss all these function values up here with all these limits which are positive, but we can't dismiss the ones which are negative because the function is approaching 0. So if I say I want a bound of a half, or negative a half, that's a bad idea because the function will actually reach that and then surpass it. So I can't choose a negative maximum because the function is actually approaching 0. Right.
For our last question.
Our last question. Determine at which points this function is continuous. So this is a piecewise defined function. On the left-hand branch we have e to the 2x, and on the right-hand branch we have cos x. The good news is these functions you can just take as being continuous. So the function is automatically continuous at all x values except perhaps where they join. So let's just write that one down first. So really this is just a fancy way of saying check if the function is continuous at 0.
And you might include here that the reason I think you stated is because each of e to the 2x and cos x are individually continuous functions.
Mm. So I said that, but
Yeah,
perhaps I
you
should write it
said
as well.
that, but yeah.
Okay, so
Okay, so if you wanted
2x. So I've made up my piecewise function out of 2 continuous branches, and we're just going to make sure that it's continuous when it joins. What does continuous at x equals 0 mean? So this is similar to the story we saw earlier on in the video. Now we have a function and we want to show that the limit from the left, or the limit from below, is equal to the limit from above, and in fact that's also equal to whatever value the function takes at that point. So there's 3 things to check here, and they all have to be equal. So these two alone, these 2 conditions, just say the limit exists. This extra condition says the limit equals what the function equals at that point. So the limit as x approaches 0 from below of f of x, well, x is negative here, so f of x just becomes e to the 2x. Which approaches 1. The limit as x approaches 0 from above of f of x is equal to the limit x approaches 0 from above. Here my function values are always strictly greater than 0, so I can take, well, f of x is just cos x in this case. And I can take the limit of this function, that's also 1. And finally I just evaluate the function at 0, and that's equal to, well, when x is equal to 0, I get cos, f of x is cos of x, this is just cos of 0, which is equal to 1. Good, they were all equal to 1, hence the function is continuous at 0. And in fact, continuous everywhere. Done.
Nice. Yeah, I think it's useful to us to remind you that, you know, if you're asked a question like this, you do want to answer the question, and typically a last line that actually addresses the question that you were asked is a good thing to do, to wrap it up. So yes, we've answered the question, we've done what you wanted us to do.
Yeah. In terms of actually passing these exams, I think we should mention that the questions are very terse. So if you've been following the online tutorials, we kind of hold your hand through the questions and we show you the path to the answer we want you to follow. In these questions, it's up to you to create your own path to the answer. So, for example, what Norman did over here was he actually created this path, this scaffolding, by defining what maximum value was. And then using that scaffolding, he can then answer a question. What I did was I wrote the definition of what it means to be continuous at x equals 0, and then I answered my question. So this alone is kind of unhelpful. I need to create some kind of scaffolding and then answer a question. So that's something you'll have to do during the class tests, because you won't have much to work with. You'll just be given a question and you have to answer it, and the best way to do that, I think, is to actually get the definitions down you need and then work from there.
And I might just say a little bit of a word about the test itself. So the test is written on a sheet of paper, usually of some color or another, and you're expected to bring some paper of your own that you're going to write the solution on. So make sure that you have a couple of sheets of paper, and it's, I think, valuable to try to aim to have something that's reasonably neat. It doesn't have to be, again, really super, flowing and so on, but it has to be readable. So try to write in a reasonably big way and be generous with your use of space. Just make your solutions kind of look reasonable and neat, and don't end up cramming all kinds of stuff in the margin or in a corner or something like that.
And certainly don't try and do the whole exam on the coloured sheet of paper.
Yeah.
That never works.
Yeah. So good luck, everyone. Thanks for watching.
Yes, and we'll see you all next week for the... Is it next week? I think we are doing
Yeah,
this
I think
again
it's
next week. We'll do
for
this again
algebra.
next week for algebra.
So much fun.
See you soon.
See you.